Hello everyone, I am Dr.VRAO. Up to this lecture in thermodynamics, we dealt with first and second laws of thermodynamics, and these laws are based on the generalizations that you never get something for nothing and you never get more than you pay for, and usually you get less. These are the generalizations for first and second law of thermodynamics, and in this lecture we are going to learn third law of thermodynamics. It is based on the generalization that perfection is unattainable. Coming to the first and second law of thermodynamics, or the first and second law of thermodynamics has led to new concepts of energy content and entropy, but third law does not lead to any new concepts. It only places a limitation on the value of entropy of a perfectly crystalline solid. I repeat, third law does not lead to any new concepts. It only places a limitation on the value of entropy of a perfectly crystalline solid, right? So, before passing on to the third law of thermodynamics, we should know one thing, that in the earlier development of chemical thermodynamics, the difficult task is to ascertain the relation between delta G and delta H. Various attempts made to ascertain the relation between delta G and delta H. One such attempt is that Gibbs-Helmholtz equation, right? These are the attempts to ascertain the relation between delta G and delta H. One such first ever attempt is that Gibbs-Helmholtz equation, right? Gibbs-Helmholtz equation. This equation is that delta G is equal to delta H plus T into dou by dou T of delta G at constant pressure, right? This is the relation between delta G and delta H as per Gibbs-Helmholtz equation, and this is the first ever attempt to ascertain the relation between delta G and delta H, right? And delta G is equal to delta H plus T into dou by dou T of delta G at constant pressure. This is the ascertained relation between delta G and delta H according to Gibbs-Helmholtz equation, right? And from this equation it is seen that at absolute zero of temperature, that is if temperature becomes 0, that is absolute zero of temperature, this term becomes 0, because when we substitute T equal to 0, this term becomes 0, right? Then delta G is equal to delta H. Delta G is equal to delta H, that at absolute zero of temperature this term becomes 0 and delta G is equal to delta H. Based on this Gibbs-Helmholtz equation, scientist Richard measured EMFs of many cells at different temperatures and observed that the value of dou by dou T of delta G approaches 0 as the temperature is lowered, right? Okay, this is the first attempt to ascertain the relation between delta G and delta H, right? This is the first attempt to ascertain the relation between delta G and delta H, and according to the Gibbs-Helmholtz equation, delta G is equal to delta H when temperature at when temperature becomes absolute 0, and when temperature is absolute 0. When temperature is absolute 0, this term becomes 0. Okay. So, according to Gibbs-Helmholtz equation, delta G is equal to delta H when temperature is at absolute 0, right. Based on this Richard, based on this observation, scientist Richard, he is the second one to ascertain the relation between delta G and delta H. Scientist Richard measured the EMFs of many cells at different temperatures and found that the value of dou by dou T of delta G approaches 0 as the temperature is lowered. That is, as the temperature is lowering, the value of dou by dou T of delta G approaches 0, right. Okay. This is the found by the Richard by measuring the EMFs of many cells at different temperatures. So, according to Richard, the value of dou by dou T of delta G approaches 0 as the temperature is lower, as the temperature is lowered. Okay. As the temperature is lowering, the value of dou by dou T of delta G approaches 0, right. So, this is the Richard's concept or Richard statement, right. And based on the Richard's data, right, third attempt was made, that is Nernst attempt, right, that is Nernst attempt, that is based on the Richard's data. Nernst made a suggestion that the value of dou by dou T of delta G approaches 0 as the temperature approaches to absolute 0. This is Nernst heat theorem, right. I repeat, Nernst, based on the Richard's data, Nernst made a suggestion that the value of, actually Richard concluded that the value of dou by dou T of delta G approaches 0 as the temperature is lowered, or as the temperature is lowering, dou by dou T of delta G approaches 0. But based on that Richard's data, Nernst made a suggestion that the value of dou by dou T of delta G approaches 0 as the temperature approaches to absolute 0, as the temperature approaches to absolute 0. This is called Nernst heat theorem, right. So, Nernst heat theorem, what is the statement of Nernst heat theorem? Nernst heat theorem, according to Nernst heat theorem, the value of dou by dou T of delta G approaches 0 as the temperature approaches to absolute 0. This is Nernst heat theorem, right. Therefore, according to Nernst heat theorem, delta G and delta H, that is when dou by dou T of delta G approaches 0 as the temperature approaches to 0, then delta G is equal to delta H, right. So, this is shown by a graph, okay. This is shown by graph by Nernst based on the Richard's data, and according to Nernst heat theorem, the delta G and delta H approaches or tend to approach each other as the temperature approaches to absolute 0. Okay. So, I shall draw the graph that is plotted between delta G, delta H versus temperature. Okay. So, I have drawn the graph, right. That is based on the Richard's data. Nernst plotted a graph between delta G values, delta H values, delta G values or delta H values, okay, right, versus a temperature, right. So, according to Nernst heat theorem, delta G and delta H tend to approach one another. Delta, for suppose say this is delta G values and these are the delta H values. Delta G and delta H tend to approach one another, This is the origin where temperature is 0, right. Delta G and delta H tend to approach one another at the temperature is towards, that is delta G and delta H tend to approach one another as the temperature at absolute 0, that is towards absolute 0, right. So, delta G, delta H tend to approach one another tend to approach one another as the temperature approaches to absolute 0, and they coincide with one another above the absolute 0, and they are coincide with one another above the absolute 0. This is the 0 temperature, and these two are coincide with the one another above the absolute 0 and run coincide with each other up to absolute 0 temperature, right, up to absolute 0 temperature. I repeat, delta G and this is delta G and delta H approaches or tend to approach one another as the temperature lowers towards absolute temperature, as the temperature lowers absolute 0, and above the absolute 0 they tend to each other, that is they delta G and delta H are delta G and delta H values are equal above the absolute 0 and run coincide with each other up to absolute 0. So, this is Nernst heat theorem. Okay. So, this this explanation is put on in mathematical formulation, that is limit T tends to 0, that is temperature approaches to 0, dou by dou T of delta . Okay, and coming to the consequences of this Nernst heat theorem, we can write this dou by dou T of delta G, that is equal to delta S. Okay, delta S. How it is equal to delta S? We know that delta G equal to VdP minus S dt. VdP minus S dt. We are putting pressure constant. We are putting pressure constant, that is at pressure constant P constant dP is equal to 0, then this term becomes 0, then dz is equal to minus S dt, then dg by dt is equal to minus S, that is d by dt of delta G is equal to minus delta S. right? Okay. Similarly, we can interpret, we can write that d by dt of delta H is equal to delta Cp. Okay, this is from this is originated from another basic thermodynamic equation, right? Okay, so we can write limit t tends to 0 dou by dou t of, instead of dou by dou t of delta G, we can write minus delta S, that is limit t tends to 0 dou by dou t of delta G at constant pressure is equal to minus delta S, right, is equal to 0, and this is equal to limit t tends to 0, limit t tends to 0 dou by dou t of delta H, that is equal to delta Cp. That is change in entropy becomes 0 when temperature approaches 0. When temperature approaches 0. When temperature approaches 0, change in entropy becomes 0. When temperature approaches to 0, absolute 0, change in heat capacities, that is delta Cp, change in heat capacities at constant pressure is equal to 0. This means that entropy of, this means that this equation or this mathematical equation states that entropy of every substance is 0 at absolute 0 temperature, right? Entropy of every substance is 0 at absolute 0 of temperature. Okay, sorry, 1 minute, there is a small correction in this statement. This equation, this mathematical equation states that entropy of every substance may become 0 at absolute 0 of temperature, right? You remember this point in your mind, right? You keep this point in your mind. Temperature, as the temperature approaches to 0, change in entropy becomes 0. That is, this equation states that entropy of every substance may 0. Entropy of every substance may become 0 at absolute 0 of temperature. But it does so in case of perfectly crystalline solids, right? Okay, I hope you got that point. Entropy of every substance may become 0 at absolute 0 of temperature, right? And it does so in the case of perfectly crystalline solids. That means that in perfectly crystalline solids at absolute 0 temperature, entropy is 0. Entropy is 0, right? I repeat, in perfectly crystalline solids, entropy is 0. That is, entropy is 0 at absolute 0 of temperature, right? And it is it holds good, it may holds good in case of other substances, but it is definitely holds good in case of perfectly crystalline solids. Therefore, we can conclude that entropy of every substance may become 0 at absolute 0 of temperature, but it does so, it definitely does so in the case of perfectly crystalline solids. That means that forget about other substances. In perfectly crystalline solids, especially in perfectly crystalline solids, at absolute 0 of temperature, entropy is 0, right? It holds good in perfectly crystalline solids. But when we go for other substances, that is not that is imperfections of imperfected crystalline solids, imperfect crystalline solids, entropy may not become 0 at absolute 0 of temperature, right? Okay, so limit T tends to 0 delta S equal to 0. Okay, from Nernst heat theorem we can conclude that limit T tends to 0 delta S equal to 0, limit T tends to 0 delta Cp equal to 0. Okay, from this we can conclude that entropy of every substance may become 0 at absolute 0 of temperature, and it is does so in the case of perfectly crystalline solids, right, perfectly crystalline solids. Okay, therefore in perfectly crystalline solids at absolute 0 of temperature there is a state of perfect order, there is a state of perfect order, that is perfect order, that is perfect order means there is zero disorder, there is zero disorder, zero disorder means zero entropy. Okay, I repeat, in perfect crystalline solids at absolute 0 of temperature there is a state of perfect order, that is ordered arrangement at absolute 0 of temperature, that is ordered arrangement means there is zero disorder, zero disorder, zero disorder means zero entropy, zero disorder means zero entropy. Okay, so in perfectly crystalline solids entropy at absolute 0 of temperature entropy is 0, but it does not holds good other than perfectly crystalline solids, right. However, you should keep this point in your mind. However, in perfectly crystalline solids if there is any type of imperfections at absolute 0 of temperature, at absolute 0 of temperature, that is 0 degrees Kelvin, that is called, such entropy is called residual entropy, that's called residual entropy. Okay, residual entropy means residual entropy. Okay, residual entropy, it is said in the case of perfectly crystalline solids. But for example, if there are any type of imperfections in perfectly crystalline solid, okay, if there is any type of imperfections in perfectly crystalline solids at 0 degrees Kelvin, such entropy is called residual entropy. Okay, residual entropy. Therefore, third law of thermodynamics is that entropy. Okay, therefore, third law of thermodynamics in nutshell, third law of thermodynamics is that entropy of every substance may become 0 at absolute 0 of temperature, but it does so in the case of perfectly crystalline solids. Okay, so perfection is possible in case of that is 0 entropy is possible in case of perfectly crystalline solids, but that perfection is not attainable in case of other than perfectly crystalline solids. Therefore, third law is based on the generalization that perfection is unattainable. Okay, I hope you learned something from this lecture. Okay, if you learned something from this lecture, you please extend your support by like, share, comment and subscribe. Thank you for watching.